Hello students, welcome back to OrganiChemVerse. In today's video, I have handpicked some of the most important questions from haloalkanes and haloarenes that collectively cover the majority of the concepts you need for your exams. I encourage you to pause the video and attempt each question on your own before watching the solution. At the end of the video, you will also find a set of homework questions to test your understanding, solve them sincerely, reinforce your learning, and walk into your exam with confidence. So let's get started. The first question is based on the order of reactivity for SN2 reaction. The given molecules have some similarity in the structure. The difference is the reactive carbon is attached to oxygens here, oxygen and sulfur, sulfur and sulfur. Whenever we have a SN2 reaction, we always go by the steric hindrance. The molecule which is less sterically hindered will undergo SN2 reaction faster as it is one-step reaction. Say if it is methyl chloride, the order of reactivity will be greater as compared to primary halide, then secondary, then tertiary halide. But the steric hindrance will not help us a lot here because the difference is with respect to the atoms attached to the carbon here. In that case, how to solve the question? For questions like this, it's better to generate the carbocations assuming that they undergo SN1 reaction. Why do we have to do that? Because a molecule which prefers to undergo SN1 reaction will not undergo SN2 reaction. So generate the carbocations for the given molecules. So what I'm going to do here, generate the carbocation on this carbon. Now, is there any way of stabilizing this carbocation? Yes, that is the reason these two oxygens are given. The lone pair of electrons present on oxygen will donate to the carbocation through plus R effect and it will stabilize the carbocation. Now, can we stabilize this carbocation? Yes, we can. How so? Because sulfur also has a lone pair of electron, right? It will also donate the lone pair to stabilize the carbocation through plus R effect. So which will stabilize the carbocation better now? So for that, let's take the help of electronegativity of the atoms. Oxygen is electronegative element, so it withdraws electron through inductive effect by destabilizing this carbocation. Sulfur is not as electronegative as oxygen, so it will not withdraw electron through minus I effect. That means it's a better electron donor. So this will donate electrons better through plus R effect, stabilizing the carbocation. That means this will undergo SN1 reaction better. If it undergo SN1, it will not undergo SN2. That means this molecule will be the least towards SN2 reaction. And where do we have it as a least? You can see it in option A. And which will be the most? This will be the most because it is not preferred to undergo SN1. So it prefers to undergo SN2. That's why this will be the first. What about here? We have both atoms, oxygen and sulfur. So it will be in between. So obviously it has to in between. And you don't have to apply all this. Just check where 2 is in between 1 and 3. See here, it's in between. What about here? No. What about here? No. What about here? No. So this way you can easily tell that the correct option is option A. The next question is based on the series of reactions. The cyclopentene molecule is treated with N-bromosuccinamide, which is a halogenating reagent, and where the halogenation always happens at the alpha position. So we have different hydrogens here. We have phenylic, we have allylic, we have homoallylic. But which hydrogen will be always replaced at the alpha position? Why so? Because the free radical formed here will be stabilized by resonance. That's the reason the bromination happens at the allylic position, and this is the allylic bromo compound formed, and this is product A. And when it is treated with alcoholic KOH, the moment you see alcoholic KOH, remember it is elimination reaction. So you are doing dehydrohalogenation. The hydrogen will be removed from the adjacent carbon where the halogen is attached, right? So you are going to do a dehydrohalogenation to form a double bond like this. So what is this? This is product B. And this is treated with Grignard reagent CH3MgBr. By now, you might know that the Grignard reagent can act as a nucleophile as well as a base. So how does it function in this case? Is there any electrophilic carbon in the reactant molecule here? No. But is there any acidic hydrogen in the molecule? Yes, there is. Why so? Because when this hydrogen goes as a proton, right? And the Grignard reagent will abstract it as a base and it's going to form a methane gas. And what happens to this molecule? It's going to form a carbanion, which will be stabilized by the counter ion MgBr. And why this carbanion is formed? Because it is a stable molecule. Why is it stable? Because it is aromatic in nature. Why is it aromatic in nature? Because it is cyclic, it is planar, and there is a continuous conjugation of electrons. You can see here, right? It can undergo resonance like this, and it is obeying Huckel's 4n+2 rule. That's why the resultant product is aromatic in nature. So this is our final product, C. Do we have it in the options? No, we don't have it in the options, but there is an option, none of these. So therefore the right answer is none of these. Many students, what they do is, if they see any, all of these or none of these, they tend to ignore that option. So don't do that, because you can get such questions wherein the option is none of these. The next question is based on the aromatic nucleophilic substitution reaction. You have to arrange the given molecules in the decreasing order of their reactivity. Generally, when we have different halogens and same alkyl group, whether it is SN1 reaction, SN2 reaction, SNR reaction, if all the groups are same, right, then the order of reactivity for different halogens will be always in this order. It will be like this. Why is it so? It's because of the bond length. The bond length for carbon and iodine will be greater, therefore it's easy to cleave this bond. That's why the order of reactivity will be always like this. But for the given molecules, you can see that the groups attached on the benzene ring is also different. So that means what? This also matters here in order to decide their order of reaction. If there are no groups over here, we would have easily told that 3 reacts faster than 2 than the 1 because of the halogen. But the groups are also different here. For aromatic nucleophilic substitution reaction, we know that as the number of these electron withdrawing groups increases, the SNR reaction order also will increase. The reactivity will also increase. You can see that in the first molecule, there are 2 nitro groups. Both of them are electron withdrawing groups. So what happens here? They withdraw electrons by weakening this bond. Hence, this cleaving of the bond will be much easier. What about here? Methyl groups are electron donating groups. The electron donating group strengthen this bond and the breaking of this bond will be difficult. What about here? We have one electron donating and one electron withdrawing. So it will be in between. So now, which case to consider here? Should we consider this case or this one? So here in this case we have to take more the electron withdrawing group, because here they withdraw electron through minus R effect. Resonance always predominates here. Therefore, the one will react faster. And where do we have one reacting faster? In option A and C. Then what do we have? 3 as more reactive. And where is it? In option C. Therefore, the final option is option C. Let's find out what are the products B and C for the given sequence of reactions. The propanoyl chloride, an acid chloride, is treated with excess of Grignard reagent. So the product must be a tertiary alcohol. So how the reaction takes place? The first mole of Grignard reagent, when it attacks, it will undergo nucleophilic substitution and it forms a ketone. This ketone is still reactive towards Grignard reagent. So the next mole will attack here. and upon hydrolysis it's going to form a tertiary alcohol like this. So this is what? This is product A, and this is heated in presence of an acid. That means this will undergo dehydration easily as it is a tertiary alcohol. We are going to get only one product and it is this. And where do we have it? We have it in option A. So wherever we have it as B, you can eliminate those options here. The final options, you can eliminate those. So the product C could be either this diol or this diol. What is the difference here? This is a syn. That means the OH are on the same side. Here the OH are on the opposite, anti side. So how to decide this? So we can do it step by step. The B product is treated with bromine, water, and NaOH. What happens first? The bromine will add to the double bond and it will form a reaction intermediate like this. Now, the water will always attack from the opposite side because of the steric hindrance. If the water attacks from here, the bond will break here and it is always the anti-addition. So you can see that if the OH is attacking from above the plane, the bromine will go below the plane. See, ultimately what should happen? The bromine should be substituted by the OH. For that, oxygen will help it to leave the molecule. It will attack this carbon like this, right? It's going to form a reaction intermediate like this. And then what happens? The water, whatever the next mole of water should attack, it will attack from the opposite side. So what do you understand from here? It's always an anti-addition. So here the OH should be out of plane. If one OH is above, the other should be below the plane. And where do we have it? In option D. So the final answer is A and D. Where do we have it? In option B. Therefore, this is the correct answer. For the last question, you have to find out which of the given two reactions is faster and what is the mechanism involved in that reaction. You can see in the first reaction, 1-chloropentane when treated with ethoxide in ethanol is forming 1-pentene. In second reaction, 3-chloropentane, same reaction condition, that is ethoxide ethanol, is forming 2-pentene. Now, which reaction will be faster? Both of them are elimination reaction. So the reaction conditions are also same. Then how to decide? By the stability of the products. Whichever is more stable between 1-pentene and 2-pentene, that will be forming faster. So between these two molecules, 1-pentene is less stable because of less number of alpha hydrogen. You can see that there are two alpha hydrogens here. That means only these two can undergo hyperconjugation, hence less stability. What about here? We have three alpha hydrogens here and 2 alpha hydrogens here. So all put together 5 alpha hydrogen. More the number of alpha hydrogen, more no bond resonance structure, more is the stability. Since this is more stable, the second reaction will be faster. So between 1 and 2, 2 is faster. Where do we have it? In option A and option D. But will it undergo E1 or E2? It depends on the reactant molecule given here. Generally, the secondary halides can undergo either E1 or E2. Then how to decide? It also depends on the base given here. The ethoxide is a strong base. It is so strong that it will remove the beta hydrogen here in one step like this. And the dehydrohalogenation is happening in one step. If it is one step, what sort of mechanism it will obey? It will obey E2. That means no carbocation formation. No carbocation means it is E2 reaction. Hence, the correct option is option A. The second reaction is undergoing faster reaction through E2 mechanism. How did we decide? By the reactivity of the reactant, the strength of the base given, and the stability of the product. I hope I made this clear, and if you still have any questions, you can drop your queries in the comment section and don't forget to subscribe the channel. Thank you.